So thank you for being here today or listening virtually if you're listening after the fact. What we'd like to share with you today is some work that's been ongoing for us for quite a while. Um, my name is Kajander, and I began as a high school mathematics teacher along the way after my doctorate. And Jennifer has a background as an elementary teacher, and both of us came together in a research context because we were working with pre-service teachers, particularly elementary teachers, and found through our work trying to support inquiry, exploration, problem-based learning, whatever label we put on it, that this was extremely difficult for many teacher candidates because they simply didn't understand the mathematics deeply enough. So if you understand mathematics only based on a series of rules that you've memorized, it's very difficult to come up with classroom lessons that support students to learn mathematics differently. And so without really intending to, we got drawn very deeply into trying to reconstruct mathematics differently for teacher candidates, originally elementary, and more recently intermediate and secondary. So the context that we're going to talk about is the province of Ontario. So Jen, if we go to that slide, and so education in Canada is provincially mandated. So we're going to speak about our own region, which is the province of Ontario. And as you see by the various dates here, we're in the middle of quite a range of curriculum revisions. So the curriculum, which is the learning expectations for the students, uh, these expectations are mandated by the provincial government, by the province. However, the textbooks are produced commercially. So textbooks are written by commercial companies that are trying to sell books. So they want the books to be desirable by the individual school boards, and the alignment of the books with the intended curriculum may not always be perfect. So there are many different visions that teachers are being exposed to uh, in terms of what's happening in our province. There's also been quite I guess, a political push towards the idea of moving back to basics, computational skills. That's not what the researchers have been advocating for. So all of this sort of sits in this milieu of various points of view about what should be happening. Our elementary curriculum, and that's typically grades 1 to 8 here in Ontario, was revised in 2020 in the middle of the pandemic. And the grade 9 curriculum was revised very recently, only just over a year ago. And it's quite different in that it is what's called de-streamed. In other words, we used to have two different pathways that students could choose as they entered high school. And now all of those students are grouped together, similar to what is done at the elementary level. And so that's posing challenges for teachers that have not typically taught that way recently, and is also putting more emphasis on the need for learning that is amenable to all students, so that students that don't think algebraically as their immediate starting point, they need some basis for beginning. So these are all some of the things that that we're dealing with. Our teacher education program is a 2-year program post-degree. So what that means is that candidates come into it after the equivalent of a 3 or 4-year undergraduate degree, which probably has nothing to do with education. So our elementary teacher candidates also typically have no math courses, or it's unusual that they do. So they would be qualified to teach elementary level with perhaps only a few years of high school mathematics, and often bad experiences in that. The high school mathematics teachers, of course, are supposed to have at least a few years worth of university mathematics. One more challenge that we have, so moving on slides, one more challenge that we have right now in Canada, perhaps it's the news has made it over there, is that there's a real emphasis being made to try to do a better job supporting our Canadian Indigenous students. And one of the things that is common in the languages of the Canadian Indigenous languages is, my understanding is that they are typically more verb based. They relate more to relationships and concrete objects and their relationship to each other and their function and form. So this is quite different from how we typically think about Western mathematics, which is typically more noun-based. So we define objects in mathematics, whereas in Indigenous language, there's more emphasis on what things do and how they move and how they relate to other things. So the idea of defining a shape as something that sits flat, so its function rather than its characteristics. And so we also have this sort of emphasis. And what I really like about some of the ideas we're going to share with you today, that while we believe truly that there are better ways for all students to learn, they also happen to support this push to decolonization, this push to support students that think that whose original languages were more verb-based, because they lend themselves to this idea of being more active and visual with the mathematics. Lisa Lunny Borden, who is cited there, is one of the eminent Canadian scholars in Indigenous mathematics education, and she has coined this phrase, visualizing and verbing. And I think that's a really wonderful metaphor for what we're going to talk about, the idea that we want students to, first of all, visualize a mathematical idea, work with it actively. So that's kind of the verbing piece. And then later on, we can formalize it and name it and so on. And so this way of thinking about mathematics actually works very well in the kinds of environments that we were already trying to develop it and support. In terms of our own background, we have been studying teacher candidates. So that's the next slide. We have been surveying teacher candidates coming into our program into teacher education for quite a number of years. Originally elementary teacher candidates, and then we began to explore teacher candidates that actually had math backgrounds. And what we found consistently over the years is that while many could execute procedures, that is, they could do computations to find answers, that they almost literally had nothing when it came to explaining why those ideas worked. They really had no idea why some of those methods and numeric and algebraic procedures actually made sense. And we felt very strongly that this was not a sufficient basis for teaching. And what was really startling to us, and that's in the second article that's cited there in the slide, is that this seems to hold true even for teacher candidates with strong post-secondary math backgrounds, which was really surprising. So I'm going to say that again. Teacher candidates, even those with significant numbers of university mathematics courses, were not able to explain using representations, using reasoning, why some of the methods that they learned in elementary and secondary school worked or made sense. They could tell you the steps, but they really didn't know why those steps worked. So that's the sort of the backstory to why we began this work, which we're referring to as representation and reasoning. I sometimes fall back on the phrase models and reasoning, which was sort of the earlier term, but the word model can also refer to a way to characterize a real world example. And so it kind of has two meanings. But if I use the word model in this talk, I generally mean a representation, meaning a drawing, a representation with some physical math manipulatives, possibly even an idea in one's head, or something that is built on a screen with technology. Anything visual that I can use as a tool to think and reason with. And it's really the reasoning piece that's crucially important. Moving on to the next slide. So in North America, a lot of this work has been referred to as mathematics for teaching, in particular specialized content knowledge. We're not going to go into the frameworks in a lot of detail, but that's really sort of the idea that we've been basing this on, that there is knowledge about mathematics that is particular to teaching, and that teacher candidates may not know as they begin a program, even if they have mathematics background, and yet we feel is really important to do a better job in supporting student learning. And there is some large scale research, including from Europe, that supports the idea that students who are learning from teachers with this kind of deep conceptual understanding do have better achievement. And that is the assumption that a lot of our work is based on, that this will support better student learning. Moving on, so the field is reasonably well defined in North America in terms of earlier grades. So at grades 1 to 6, it's relatively common to find teachers that have some sense of what does it mean to teach with manipulatives, with models, using base 10 blocks, for example, to help students understand place value and the properties of number. There's a little bit less work at grade 7, 8. The book that's cited there is one that I wrote with a teacher colleague to support extending the idea to the idea of using representations to learning more at the upper elementary grades, and it kind of just barely reaches into grade 9. But we really sort of, I guess, in a sense, hit a wall when it came to, or I did at least, when it came to extending these ideas to the secondary level. There's, I think, also more reticence amongst secondary teachers, and I meant to ask at the beginning how many people here were actually classroom teachers. But certainly in North America, there's more reticence, I think, in secondary for teachers to teach with manipulatives, representations, and so on. There's this sense that they don't have time. And we even in a research context came across teachers that felt that this was somehow uh, not mathematical, that these were toys, perhaps, that, students were being encouraged to play with. And we absolutely disagree with that point of view. We believe that this process of using representations as tools to reason with is deeply mathematical, and in fact is mathematics, that this reasoning piece is what is missing when we tell students numeric and procedural methods, that they think that mathematics is something we just have to memorize, and they don't have a sense of what it means to reason mathematically. So we argue that this is deeply and fundamentally mathematical. So in terms of the benefits, we hope that you will see some elements of the following list in the examples that we're going to give. So on the next slide. Our original goal was that we would really be able to support the knowledge of our teacher candidates better, but we really believe that these methods are better for students, for classroom students as well. One of the other benefits is the idea that they provide what we're calling a lower mathematical floor, so that if you start perhaps in a high school class by presenting students with an algebraic process, many students will just, they're done, like they've checked out already. I mean, it makes no sense to them. They kind of give you the body language of like, okay, that's it. This isn't for me. But some of the activities that we have done are less intimidating and have more buy-in, I think, to more students. And I say this from the point of view of an experienced high school teacher. So the first activity we're going to share in a little while literally begins with us giving students out bags of materials that look like this and asking them to play around with them in a certain way and make rectangles with them. There's no algebra visible in that to students. And it has a playfulness that students are willing to engage with. So we really find it draws more students in, and then once they're in, then they're in. Then they're already creating mathematical objects and entering at least some level into the conversation. Uh, Moving on. So these are some of the things we're hoping that these activities will support. Um, I think it's also just plain more interesting. We don't talk about this very often. We talk about student achievement and all kinds of other good things. But at a certain level, it's also important to have students that are engaged with the ideas. And if you watch, a typical high school classroom, certainly here in North America, with a teacher standing at the board or working on a computer or whiteboard and, literally listing out algebraic statements as sets of rules, the students don't take very long before their eyes are all over the place and they're on their phone and they're whispering, and there's just the engagement piece isn't there. Um, so I think it's something we don't talk about enough, but it's much more engaging to be playing with mathematical ideas. And uh, I hope you will perhaps have a little sense of that playfulness in what we're going to do in the second half today. Okay, so we really want to spend a lot of time today giving you some examples. Um, we've heard people talk about different ways of learning mathematics, and I often find that until you get into the examples, you don't really know what the meaning of all of that is. A number of times I have seen a publication of a new book in math for teaching for secondary teachers. I can think of 2 or 3 times that that's happened in the last few years here in Canada. And I eagerly order the book and I open it and I discover that it's actually based on, first of all, giving students the procedures and then drawing a picture to show how it makes sense. And I want to be clear that that is not what we're talking about here. Jennifer's actually coined a name for this, which I think is lovely. She calls it procedures with pictures. And what we mean by that is that after the fact, we're drawing a picture to say, oh, by the way, this is how this rule makes sense and this is what's happening. But what we never really talk about is that we still have to tell students the rule or the method using that same old teacher-directed method of, first you do this, and then you do this, and then you do this, by which time we've probably lost quite a number of the students. And so we want to be clear that what we're striving for is not that. It is not procedures with pictures. It is beginning with a representation, perhaps with some math manipulatives, with a context, with materials, with a model, with some ideas, and saying, okay, if we work with these materials in a certain way, if we reason it in a certain way, what do we notice? And through questioning from the teacher, what we would want is that students would begin to construct the ideas that we're trying to get them to see. And that's really different fundamentally than, first of all, telling students the rule and then applying a picture afterwards. Because in that first context, there isn't really the same level of reasoning. What we're asking is that students are deeply involved in the reasoning process based on using representations and materials, and that the teacher's job is to sort of point that reasoning in the direction through the questioning, through the activities, through what we're asking them to do. We still want to get to the generalizations. I think that's another thing that's really important. One of the criticisms of learning this way is people say, yeah, but we still need them to learn to factor. We're not saying that students shouldn't develop eventually the algebraic techniques. What we're saying is that we want them to do that with reasoning and understanding, so that if they forget a method, they have something to fall back on. And that while they're doing the method, they have a sense of what's going on. Why is this method working? But eventually, we do still want students to generalize. We just want them to generalize based on these experiences. And I think that's the key piece. It's not like we're going to put the materials away. So I get teachers saying to me, well, when should I take the manipulatives away? It's never. Students will drop the manipulatives when they are ready to think abstractly, because it is quicker to write out an algebraic statement than to work with a model with materials. So they will naturally begin to work in a more abstract way when they are ready. But if we take the materials away too soon when they're not ready, then the only thing students are left with is memorizing again. And that's the very thing we're trying to get rid of. So the two examples we've chosen, the first one I've used many times myself in my own grade 9 classroom as a teacher. So I know that students respond very well to this. And we are currently offering this as an example to pre-service high school teachers. And I think it has many of the elements that we've talked about here. The second example is one that's a little bit more of a work in progress, but some of my pre-service teachers did some really wonderful work on it last year. So I want to sort of share that secondly to whet your appetite. Coming back to the first example, thinking about a grade 9 classroom, this is predicated on the idea that students would have already learned certain things at the elementary level. And certainly what I found in my own classroom teaching, now this was some years ago, was that that wasn't necessarily true. And so I had to actually go back and review and deepen students' understanding of whole number multiplication and develop some of the models for whole number multiplication before we could move to multiplying algebraic binomial quantities. Ideally, some of that whole number multiplication work would happen at the elementary level. This is what I would hope that this would be happening by now. But even now, we know that this is inconsistent and that not all teachers in our region, at least, teach this way. So if you are interested in trying some of these things, or perhaps you already are, you may know that it is probably necessary to ensure that students have a sense of how they can model whole number multiplication before we move on to thinking about algebraic expressions. So we're going to start there. So at this point, we're going to basically take a sort of a workshop format. And Jennifer, who is a whiz at this, is going to sort of mirror what we're talking about and exploring using an online environment. Having said that, I still believe that there is some benefit to working with concrete materials. So if we were doing this in person, and I was magically in Europe right now with all of you, I would probably be handing you out bags of materials at this point and asking you to work with the concrete representations. There's actually some literature that I've seen that it actually uses different parts of your brain if students work with concrete materials as opposed to working only virtually. So I still have some belief in that. So we're going to start at a much earlier grade level, kind of primary grades, and we're just going to think for a second about whole number multiplication. So Jen, if we can just see an example of that when you're ready. So first of all, just thinking about single digit whole number multiplication. Can we go a step back and look at something like 4 times 6 or 2 times 3 or something? So I want you to just think in your mind for a second, and if you have materials handy, that's great, but you may well not. A piece of paper will work just fine. Just if you could just draw a quick picture, perhaps on a piece of paper in front of you, what representation might you draw to represent any single digit multiplication? So 4 times 6, for example. You can use a simpler one, 2 times 3, even if you don't want to draw that much. What are pictures? And I'm shooting for several different pictures here, ideally 3. What ways could you represent 4 times 6 on a picture? And you could just take a second and sort of sketch that on your own piece of paper. And I just want to add here while we're just paused, would be very happy with a fairly informal interaction here. So if you have something you'd like to say or question or add, we do have some time set aside at the end, of course, for discussion. But as we're moving along, if there's something that you'd like to say, feel free to ask or raise your hand. I think Barbara, I think, is monitoring the chat. So if you have something that you just want to ask about, feel free to do that, and ask and interrupt at any point. Uh, it gives us a sense of if you're kind of where you're at in terms of what we're saying, if we're kind of all in the same lines of thinking here. So perhaps you've had enough time to think about that. So one way to think about 4 times 6 is to think about 4 groups of 6. And that may be one of the things that you thought about. Another way might be to think about 6 groups of 4. And if you have both of those pictures, you'll notice that they're actually different, right? 4 groups of 6 is a different picture than 6 groups of 4. And what I find that we really have to sort of push students to come up with is another way of thinking about this, which is to think about 4 times 6 as a rectangular area. That is a rectangle that is 4 units in one direction and 6 units in the other direction. In other words, it's what we call in North America an area model. And I'm curious if this is something that is familiar to everyone as a structure for thinking about multiplication. And of course, it's very similar to the other ways of thinking about these products, but the units are collected into this rectangle. And what we can push students to really think about here and observe is that the two numbers that we are multiplying form the side lengths of this rectangle. And if we fill in the space, that's the product. That is the answer. And that fundamental observation is what the area model can tell us. And immediately we see that it really doesn't matter whether we have 4 times 6 or 6 times 4. So immediately we get a property for free here, right? We get the idea that multiplication is commutative. We don't have to define it. Students don't have to memorize it. It's obvious from this model that, we can take that rectangle and move it around and we still have the same amount of space within it. So we get some things for free when we think about multiplication this way. Okay. So this is the area model. And if you were teaching elementary, it would be really important to have students understand this model, because as you're going to see today, this model takes us very far, well into the secondary grades in terms of understanding algebraic processes, which is what we find kind of exciting. So moving from single digit numbers now, we can start to think about 2-digit products. So for example, 23 times 14 can now be modeled using this same area model. Again, we think about the two numbers as the side lengths of a rectangle. And please, if you're able, feel free to sketch this on your own piece of paper as we're talking. How would you fill in the space of that rectangle? And if I was working in person with students, I would provide them with materials. So for example, these are base 10 blocks that are available. Perhaps you have them as well. So we have individual units. This represents 1. We have this length of 10 of the individual units. So this is a group of 10. Sometimes it's called a long. So it replaces 10 of the units. So in other words, this would be a 1 in the second column of a number. And then we have this region that is 10 by 10. So this is the hundreds piece. It represents a digit in the third column of a number. So this is 100 of the little units. So as we're filling in this rectangle, students can actually do this not on paper, but by using the base 10 blocks. And 2 of these hundreds pieces fill in that blue region that Jen has modeled or started there on our representation. right? So those two green squares represent the two of these hundreds pieces, a region that is 10 on the one side and 20 on the other. And I think you can see that comes from the 10 of the 14 and the 20 of the 23. And we can continue to fill in the space using the base 10 blocks or using online manipulatives. So what we see with the 10s there that Jen is filling in, that they are a length of 10, but the other side is 1 unit. So we can line them up as measured against the 4 units there of the 14 and the 3 units of the 23 to fill in those rectangular regions. And then interestingly, the corner that Jen is about to fill in is formed by the edges of those blue regions. And this is really, really interesting because this is exactly going to lead us now into our next algebraic examples, the role of those two blue areas and how that is split is constructing that yellow rectangle in the corner that is 3 times 4. So if we were doing this with elementary students, and I do this with pre-service elementary teachers, I now say to them, well, what are the subproducts of each of those regions? So we see that the green region is actually 10 times 20, and we can see that in the numbers. And the two blue regions, we have 3 times 10 and 4 times 20. You're so good at this, Jen. I'd have lines going all over the place. And then we have our corner region there as 3 times 4. And if I was doing this with elementary students or pre-service teachers, we would take a long time right now and really unpack how those subproducts relate to the original numbers. And then eventually, how this gives rise to a standard computational method. And so depending on what method you typically use to multiply 2-digit whole numbers by hand, I now think of multiplying products like 23 times 14 as 4 different numbers added up. The standard North American method kind of groups some of them together, and you have this little regrouping step that students never understand. And so we actually force pre-service teachers to make the connections from the model to the subproducts here that are written in, to how we might write those out using a list of actually numeric calculations. So 10 times 20 plus 4 times 20 plus 3 times 10, right? And then how those can be paired up to actually give rise to what we call the standard 2-digit multiplication algorithm. And typically our pre-service teacher candidates, I'm embarrassed to tell you, never knew, a lot of them never knew why that multiplication method really worked. And so this is kind of brings that to light. But the reason that I wanted to share this here is that what we see now, or what we're going to see in a minute, is how this directly allows us to develop some standard algebraic processes that are typically taught in a teacher-directed way at the high school level. One of the complaints teachers have about teaching this way is they say, oh, it takes too long. I don't have time for this. But I think what you may see here is that once we understand 2-digit multiplication this way, multiplying binomials in algebra, quite frankly, is exactly the same thing. We can do it with an area model and we end up with the same 4 subproducts. And students can understand that and they can construct it, and they don't need a rule to do it. So there's a rule in North America for how students are supposed to multiply things like x plus 2 times x plus 3, and they're supposed to memorize it, and they think they're supposed to do it in a certain order. And it's very confusing and they don't really know why. And the worst part of the rule is it doesn't generalize. You can't use that understanding to multiply trinomials times trinomials. It's like you have to start all over. So it really doesn't get you very far. On the other hand, if we think about the area model as a way to multiply this kind of expression, then the result is kind of obvious. So we're going to jump now to a grade 9 classroom, or perhaps a pre-service intermediate or secondary level classroom in a teacher education program. And of course, this activity would happen within a number of other activities if we were really working in a classroom. So we're just jumping right in the middle of a unit somewhere where we might be wanting students to learn some procedures for working with quadratics. Okay, and one of the standard procedures that is still taught, certainly in Canada, is we expect students to be able to simplify expressions and factor quadratic expressions manually by hand. Now, we can debate that at some point, whether that's a good use of students' time or not, but the reality is that that is still an expectation in our curriculum. So at some point, students need to develop some facility for it. But what we would like to argue is that it would be more useful if they did that with some understanding. And so the activity that I typically do is to provide students with literally bags that look like this, bags of algebra tiles. So algebra tiles are representations of algebraic terms. So the green terms on the screen, I have them in a physical manipulative here. Oh, beautiful. Can change in size. And that is the whole idea of a variable, that the value of the variable can change, right? So this is distinct from an unknown where there is one particular value. And that also something that needs to be discussed, that these variables represent an amount that can change and we don't know what it is. So the green lengths on the screen change, and as they change, so does the blue square. So the blue square represents what I'm holding up in front of me here, the orange square in the pieces. So the X length is one side length of this square. So in this hand, I have an X piece, which is green on the screen. And in the other hand, I have a region that is X times X, in other words, X squared. And that's the blue space on the screen. And you see the way Jen is lining them up. The lengths agree. So as the green lengths grow or shrink, so does the X squared length. So this visualization of these two changing is really important. But what you also notice is that while this is happening, the units, in this case, the little yellow squares, are not changing. So the units are staying the same size. They still represent whole numbers. Okay, so the activity that we have done and that we'd like to just try with you briefly. Again, if you have access to some online environments for algebra tiles, feel free to use them. If you have access to physical materials, feel free to play around with them as we go. If you don't, which you may not, just, a piece of paper and a pencil, and you can sketch, sketch your representations on a piece of paper. But we really encourage you to sort of think along with us as we go, because it will, I think, have more value. So the activity that I give to students is I prepare a bunch of these bags, and it really doesn't take very long. You have some ideas in your mind of some simple quadratics, and you put the representations for them in the bags. And of course, I always like to put in a few that are not actually factorable. Textbooks never do that, and they leave students with the impression that every quadratic in the world can be factored, which of course isn't true. So I like to put some in that, you can't do anything with. And I say to them, okay, so what we're going to do here is take these representations and see if you can make them into rectangles. So using all the pieces in the bag, can you rearrange the pieces to make an exact rectangle with no pieces left over and no gaps? Now you notice that there is nothing in there that involves any obvious connection to algebra. It's kind of like a, let's play with this idea. And so there's the low mathematical floor, right? There's the visualizing and verbing. Students are seeing something, they're playing with it, they're moving around. There's no sort of algebraic rule that we're beginning the lesson with that causes some of them to, check out completely. So I'm going to just pause for a second and give everybody a chance to just think about, so the materials I'm holding up here are the ones that are on the screen. How would you rearrange those materials into a rectangle? Perhaps you can just sketch it quickly on a piece of paper. And if you're quick, that might be very easy. You might perhaps enjoy trying another example. Um, Jen, can you maybe put those other examples up? X squared plus 7x plus 12. Oh, you've got them. Okay. So here's a couple of other examples. If the first one has gone quickly for you, again, you'd have to provide yourself with sketches of an x squared piece, 7 of the x pieces, 12 of the units, and so on. So let's go back to the visual representation then of x squared plus 5x plus 6. So what you might have found yourself doing here is thinking about how could you split up the green pieces into two groups in such a way that we have constructed this space in the bottom right-hand side that exactly allows us to fit in the units. Right, so that's the kind of reasoning. So students will start out just using trial and error. They'll just try different things. And then after a while, you might say to them, well, okay, is there a way to know? Is there a way to know how to split up those green pieces? But can you predict it? Like, do you have to just do it with trial and error? Or is there a way to kind of know you know, what the two groups would be? And students can begin to co-construct the idea that, well, okay, so the yellow pieces there, they form a rectangle. And so the two numbers that form the rectangle sides, they have to multiply to give the number of yellow pieces. And so those are like the two groups. So we have to split the green pieces up into these two groups. And those two groups have to multiply to give us that yellow rectangle. And if you can't do that, well, then we can't make a rectangle. So you notice in that explanation, which is a very rough paraphrase of what students might say, that is exactly the rule for factoring a simple quadratic that we teach students, right? So we teach them this crazy rule that's something like, well, the bx term has to be split up into b1 and b2, and b1 plus b2 equal b, and b1 times b2 equals c. Like, what does that even mean? I mean, what I just said, if you're familiar with it, is exactly what we just did visually. But I think, to me, it is so much more obvious when we work with the visual representation. Now, eventually, of course, students will be able to do this in their mind. They will immediately know that that middle term, in this case, the 5x, is going to get split up into two groups, and that the two groups have to multiply to give us the rectangle in the corner. And they can just do that numerically. They don't need to draw the representation. But what's going on as they're doing that is that their mind is drawing from this internalized, visualized representation. And eventually it becomes automatic for them. It becomes an algebraic procedure. But that is constructed at their own pace. Right. So I truly believe this is sort of deeply constructivist learning, in the sense that students are choosing when to generalize, when to move to a more abstract, formal, mathematical, algebraic process with meaning. And if they forget, they have something to come back to. I don't know if anyone got to the third example. Jen, do we have a picture of x squared plus 6x plus 9? Ah, brilliant. Okay. So here were the other two examples. And of course, what we then want to move to with students is get them to think about, so once you have created this rectangle, what have we really done? Right? So we have created a space that is the answer to this product. Well, what's the product? Well, the product is the length of each side. Right. And so again, this would be a whole lesson that we would take at the grade 9 level. I'm sort of assuming that people are relatively familiar with this mathematics, but we would spend a lot of time talking about, okay, well, so what are the side lengths of this rectangle? And how do we represent those using algebra? And how can we go back and forth? So of course, we can use the same representation to go the other way. We can say, all right, we have x plus 2 times x plus 3. How do we know what that is as a simplified expression? And this is where it's exactly the same, I think, as you can see, as whole number multiplication. We have exactly these same 4 subproducts that we have in whole number multiplication. There's a direct connection there in terms of one of them is 2 times x, one of them is 3 times x, one is x times x, one is 2 times 3, and so on. It's exactly the same 4 subproducts, and that we can add those up in any order. And that works for all of these different examples. Just want to point out very quickly, and we don't have time to go into this, but the third one, of course, is a perfect square. And again, this allows another idea to be constructed. Like, how do we know something's a perfect square? And students can tell you, well, it's a perfect square because the 2 groups have to be the same, because it makes the piece in the corner a square, and the 2 side lengths have to be the same to make a square, right? They can tell you, they can construct this idea. And knowing how to construct a perfect square algebraically is very important, because that's, of course, the basis of changing a quadratic function into vertex form, which is another one of these intractable procedures that we tell students the steps for, that they remember to get to the test and then promptly forget a week later. And it also allows us to develop the quadratic formula, because the quadratic formula is, in fact, a generalization of vertex form, of putting a quadratic as a perfect square and then being able to solve it from there. So this perfect square idea and being able to construct that perfect square is something that is, again, going to take us into another series of really important developments and activities. So that's a whole talk in itself that I don't want to get into today. So we have one more example, and this is one that has really bothered me for a number of years. I have to tell you that I've always felt that to have meaning in mathematics learning, that we had to be able to explore the ideas this way, using representations, using mathematical reasoning, and that needed to be transparent to students, and that ideally we would like to continue to support this kind of learning where students could construct the ideas themselves. But the procedure for factoring quadratics of this form, of this second example, where the coefficient on the x squared is not 1, so for example, 3x squared, the standard procedure in North America for doing this is very obscure. And I don't know if you use the same procedure typically there, but in North America, it's called factoring by decomposition. And the steps also involve splitting up the 11x, but in a way that equals the product of the first and the last coefficient. And it's many steps for students to remember. They don't know why they're doing it. And the thing that's actually the worst that I find is, after you get students to practice this procedure a zillion times in grade 10 and 11, they're so used to doing it that they even factor quadratics that are simple using the same method that you don't need it for. They lose track of the sum product method that we just explored, and they do all of their factoring this way, which isn't necessary at all. And so this particular technique has been bothering me for a long time. And I've gotten as far as being able to model the standard method using algebra tiles to show students what's happening. But that, as I said at the beginning, that really comes down to procedures with pictures, in the sense that we still are starting with the procedure and we're just drawing pictures to show what's happening. But I've really struggled with coming up with a way to have students construct the method of factoring quadratics of this form, where a, that is the coefficient of x squared, is not equal to 1. And so for several years now, I have thrown this problem out to my pre-service high school mathematics teachers. So these are people with recent high-powered math backgrounds, undergraduate math degrees, and so on, coming into teacher education to be a high school teacher. So their math background is much more recent than mine. And for several years, they haven't been able to do any better with this than I have until last year. So last year, one of my teacher candidates proposed a method for factoring this kind of quadratic based on using representations and reasoning, which generalizes to an algebraic method, just like the standard one, but is not the one we typically teach. It is not factoring by decomposition. And I think this is really ultimately the benefit of teaching in this way, is that now and then students will really construct something original that is so exciting to share as a teacher. So I just wanted to end by kind of sharing this method with you, which I think has a lot of potential and works just fine, actually, as a numeric method, works, or as an algebraic procedure, works every bit as well as the standard decomposition method, but I think has the benefit of being more constructible visually. And what's really beautiful about it is it's actually a generalization of the first method. It's not a new method. It's just a little tweak to the first method that makes it work for quadratics in general. And if that's not mathematical, I don't know what it is. That just feels like, exactly what mathematics is, right? It allows us to take one idea and generalize it to something that is more complicated. And so the sort of the stroke of genius that this student came up with, and I think this would be something we would probably have to kind of share with students just to sort of germinate the activity, is to take the a value, which in this case is 3, right, the coefficient of the x squared term, and use that number to construct a square of the x squared terms. So right now, the x squared terms form a rectangle. There's 3 of them. I'm looking at the top left-hand corner of this model, right? So what if, so of course we've already solved this by representing it as a rectangle. What if we made that region a square? What would we have to do to make that region a square? So I think what you can see there is, if we take the coefficient of x squared, which in this case is 3, and we multiply the entire expression by that number, we will construct a square in the region of x squareds. So what Jen is doing here is she's multiplying that top half of the expression by 3. So she's making 3 copies of that first row of tiles. And you see the blue region is now a square, which was the intent. And of course, now we have to multiply everything else by 3 as well, but that's okay. And so let's just look at this model for a second. What we have here is the original expression multiplied through by, in general, a. In this case, a's value is 3. And the reason that we're doing that is to make the blue region, that is the x squareds, a square. Okay, so far? So I want to just take a little bit of time and let everybody think about this. There's kind of 2 ways that we could proceed at this point. One way is to just simply, in our minds, and this is the way Jen is typing it right now, in our minds, just literally rethink about the unknown. And Jen, could you add one more line in there? So the first expression that Jen has there is that she has multiplied everything by the 3. Okay, so this expression is 3 times the original one. But Jen, can you just now type a new line where the middle term has the 3x piece in brackets? So switch the 11 and the 3 in a new line. And I think what you'll see by writing it this way is that what we've really done, in a sense, Sorry, Jen, just I'm being picky, but can you put the 3x in a bracket and the 11 in front? What I'm trying to have you see here is that we've really, in a sense, replaced our unknown of x by something that is 3x. So our original representation of x, if you think about a length of 3 of them, we could actually think about that as if it was a new variable. So one way of thinking about the above expression would be to say let w equal 3x. So our variable isn't x anymore, it's w. So w replaces all of the instances of 3x in the expression. And if you do that, and again, feel free to do this, on a piece of paper yourself before we give it away. Jen's typing it, but you don't have to look up. You can try and do it yourself first. Go ahead and type, Jen, but I'm just challenging people to try it themselves on a piece of paper first. What you'll see here is that we now have a quadratic of the previous type, of the exact sum product type that we already looked at. And so we simply need to find two numbers that add to 11 and multiply to 30. And in our minds, if you sort of mentally think about putting an outline around each of the chunks of 3x, each of those lengths of 3x is now a w. So the picture as well exactly aligns with the previous method. And so if we think about the quadratic that way, that's easily factorable using what we already did. So it's w plus 5 times w plus 6. And we can, again, exactly find that in the representation. Right, so the width on top there is our w plus 5, and the height is w plus 6. And the region in the corner is 5 times 6, which is 30. And there are our factors. And all we have to do now is put the 3x back in. And remember that this is 3 times as much as what we want. So we have to then divide by the 3. And the other way of going around it is just to simply keep the 3x in a bracket as if it was the variable, and again, proceed to factor in the same way that we did before. I had never seen this method before. I was astonished by it. At first, I didn't understand it. I had no idea what the student was doing. And then after I tried it a couple of times, and I realized that the important piece was the idea of making the squared terms into a square region. That's the only thing we have to sort of really keep in mind to make this method work. And once we have done that, what we really have is a general form of a representation exactly the same as the previous example, because the squared region has a coefficient of 1 as a result. So we have a few more examples. If you don't believe this works, there are a few more examples you can play with on your own if you like. The second one is interesting because in the second case, if you actually create the representation, the area model just through trial and error, you find that the square terms form a rectangle that is 2 by 3. And so you think, well, what do I do to make that into a square? Well, you can still multiply it by 6. It just makes a bigger square, because if you think about multiplying by 6, it's like multiplying by 2 in one direction and 3 in the other direction. And you do end up with a 6 by 6 square. And then again, the method is exactly the same as in the previous. So again, just to reiterate, the method is to make the x squared region into a square by multiplying by a, and of course we have to multiply everything through by a, then our unknown becomes a times w. So in the first one, it's 2x, and in the second one, it's 6x. And we can either think about that unknown in a bracket or actually replace it with something, and then it's exactly the same factoring method as what we did previously. And then we re-represent it back as x's, and of course we have to divide through by a again at the end. So I think in terms of a technical method, this is no more procedurally difficult than factoring by decomposition. But what I think is kind of brilliant about it is that it students can actually explore this using the algebra tiles and work through the steps, at least in parallel to developing the algebraic steps. They can work through it visually as they go. And make some sense of why they're doing it. And I think best of all, it isn't really a new method. It just allows us to use the previous method by making this little transformation. So we don't end up with a situation where students are using a harder method than they need to factor simpler expressions. So these are just some little snippets of some of the environments that we've been working on. I have written up some of these things, and I do have another book coming out into 2023, which is currently in press. I think the citation there is at the end of the PowerPoint. Anyway, it's not out yet, but it should be out in 2023, and all of the methods that that we were talking about here are written up in this book. So I'm kind of excited about it, actually. It is different than the first book in that it is more directed to teachers that do have some math background. The original Mathematical Models for Teaching book is more directed at elementary teachers who don't necessarily have mathematics background, but this one is written a little bit more from the point of view of a high school teacher who has some facility already with the procedures, but needs to develop the ideas of representation and reasoning to support this kind of learning environment. So I think we'll stop there, and perhaps we can open it up for questions and discussion. Happy to talk more about the examples if anybody's interested, or anything else that you might wish to bring up. I'd be delighted to hear if anybody is already doing some of this kind of work with either in their own classroom or perhaps with pre-service teachers that you're working with, or doing any other related research. And I guess the one other thing that we'd be curious about, especially the second method, if anybody actually tries this, because this is pretty new stuff. Like this is, I would say, within the last 6 months or 8 months that that a student even proposed this to me. We'd be curious as to how students, teacher candidates that you've worked with respond to these methods, and whether they find them helpful or interesting in classroom practice. So we'll stop there and open the floor to anything anybody would like to ask or talk about.